So, think about the future of global industry for just a second.
Okay, yeah.
Like, what actual physical image comes to your mind when I say that?
Right. You probably naturally picture, I don't know, massive legacy smokestacks towering over parts of Europe.
Exactly. Or maybe like those sprawling, hyper-automated mega factories stretching all across Asia.
Yeah, that's usually the default image we all have.
But if you're picturing either of those, you might actually be looking at the completely wrong hemisphere.
Which is pretty mind-blowing, honestly.
Right. Because
Right.
the data suggests that the next industrial superpower, it isn't going to be built on a foundation of coal or gas or imported oil.
Not at all.
The economic center of tomorrow might actually be powered entirely by like the blazing sun and sweeping winds of East Africa.
Yeah, and we have just completely hardwired our brains to link industrial capacity with fossil fuels.
Oh, 100%.
Historically, burning ancient carbon was just the absolute prerequisite for lifting a nation out of agrarian poverty and into industrial might.
It was the only way it was ever done.
Right, but the underlying mechanics of energy production have shifted so radically in just the last decade.
Yeah.
That old developmental playbook is, it's practically obsolete now.
It really is. And so, welcome to this deep dive. Today, you and I are going to unpack a remarkably detailed roadmap for the future of global energy.
It's a fascinating one, too.
It really is. Our mission today is to explore how emerging economies can do something entirely unprecedented, like completely bypass the fossil fuel age and jump straight into a hyper-efficient green industrial revolution.
Which all sounds like sci-fi, but it's very real.
Exactly. We are basing our entire conversation today on a rigorous techno-economic analysis. And I'm going to give you the exact full title of our source for this deep dive, just so you know the specific research we're pulling from.
It's a bit of a mouthful, but yeah.
It is, yeah. It's called Energy and Economic Leapfrogging: Strategic Pathways for Sustainable Energy Industry Transitions in East Africa's Emerging Economies.
The title is super academic, but the implications are intensely practical.
Oh, absolutely.
Like, we aren't just tossing around high-level, feel-good climate goals here. This deep dive is really about connecting the hard macroeconomic realities of emerging markets with actual on-the-ground engineering.
The stuff that's required to physically rewire an entire national grid.
Exactly. This study provides hourly resolution modeling of power, heat, transport, and industry sectors. And it does this over a span of decades.
It's basically a mathematical proof of concept for a complete systemic overhaul.
That's a great way to put it, yeah.
And the sheer massive scale of this transition is what I find so fascinating. We are not talking about subsidizing a few residential solar panels here.
No, not at all.
We're talking about architecting an entire national economy from the ground up. But to truly understand how East Africa becomes this futuristic energy hub, we really have to look at the immense friction of their current reality.
Right, you have to know where they're starting from.
Exactly. So where exactly is the starting line for this transition?
Well, context is everything, and the demographic trajectory here is just staggering.
Yeah, the numbers are huge.
They really are. So this study focuses on 3 specific emerging economies: Kenya, Uganda, and Tanzania.
Right.
And we refer to them collectively in the data as the KUT region. By the year 2050, these 3 nations are projected to have a combined population of around 300 million people.
300 million, that is just rapid, explosive demographic growth.
It is. And with that comes a massive, unavoidable surge in energy demand. And their current infrastructure simply cannot support it.
No, because their current energy mix relies heavily on a highly localized, deeply entrenched system of, unsustainable biomass.
Yeah, and the dependency there is massive. Just to give you the numbers, for Uganda and Tanzania, biomass accounts for 87% and 76% of their final energy consumption, respectively.
Wow.
And Kenya sits at about 63%.
So we are talking about a system where the primary fuel source for heating, cooking, basic survival is incredibly inefficient.
Right, and it's terrible for respiratory health, too.
Yeah, not to mention it's a primary driver of regional deforestation.
Exactly. Transitioning a population of that size off an entrenched biomass infrastructure, it requires immense behavioral and infrastructural shifts.
It's a monumental task.
And furthermore, on the electricity side, Uganda relies almost entirely on hydropower.
Right.
Which is really vulnerable to climate-driven droughts.
Right. If it doesn't rain, you don't have power.
Exactly. And then Tanzania still gets the vast majority of its grid power from imported fossil fuels.
Okay, let's unpack this because when I look at that starting line, the core idea of this study, this leapfrog concept, it immediately reminds me of the telecommunications shift in Africa decades ago.
Oh yeah, that's the classic comparison.
Right. Rather than spending billions of dollars and decades of time stringing up physical copper telephone lines and wooden poles across the continent just to mimic the Western grid, what did they do?
They just skipped it.
Exactly. Many African nations just skipped the landline phase entirely. They jumped straight to mobile phones and decentralized cellular networks. So the central thesis here is that these nations can do the exact same thing with their energy and industrial infrastructure, like skipping the carbon-heavy coal-fired industrial revolution that Europe and North America slogged through and jumping straight to a cutting-edge, decentralized green grid.
If we connect this to the bigger picture, the telecom analogy is perfect because it highlights the advantage of not having legacy infrastructure holding you back.
Right, no sunk costs.
Exactly. If you don't have billions in sunk costs tied up in a massive coal or gas infrastructure, you aren't forced to protect it.
You can just adopt the frontier technology immediately.
Exactly. And the hourly resolution modeling in this study demonstrates that an energy leapfrog isn't just a hopeful theory. It is mathematically and mechanically the most rational pathway available.
So they don't have to follow the carbon-heavy footsteps of the global north to achieve industrial prosperity.
No, they really don't. And to prove that, the study models three very distinct futures for how the KAT region could develop over the next few decades to handle this population boom.
Right. It lays out the actual policy choices on the table.
Yeah, the researchers map out a spectrum of ambition, basically. First is the current policy scenario, or CPS.
Which is the baseline business as usual approach, right?
Yeah, correct. It relies heavily on scaling up fossil fuels to meet that surging demand with zero price penalty for carbon emissions. It basically mimics the 20th century Western model.
Got it. And then you have the middle-of-the-road approach, the delayed policy scenario.
Right. The DPS introduces moderate ambition. It implements some carbon pricing around 2035 and slowly pushes for more renewables, but it maintains a significant reliance on legacy systems.
So it's a transition, but a pretty sluggish one.
Exactly. And finally, we have the best policy scenario, the BPS. This is the highly optimized, aggressive pathway aiming for a 100% renewable energy system across all sectors by 2050.
Meaning the total phase-out of both fossil fuels and unsustainable biomass?
Completely, yeah.
Okay, wait a second. I have to push back on the economic modeling here because this is where theory usually collides with reality.
Fair enough. Let's hear it.
Well, whenever we read about a whole country transitioning to 100% green energy, it is almost universally pitched as a massive financial sacrifice.
Right, like a burden.
Exactly. It's framed as something you do for the good of the planet, despite the crippling cost. But this study claims that the most ambitious 100% renewable plan, the best policy scenario, is actually the cheapest option by a wide margin.
It is, yeah.
But when we factor in the notorious supply chain bottlenecks and the massive risk premiums associated with mega projects in emerging markets, how does the study justify claiming the green path is the cheapest?
Oh, it seems counterintuitive at first. But you have to look at the fundamental difference between the cost structures of fossil fuels versus renewables.
Okay.
The study isolates the projected cost of electricity generation. Under the fossil fuel-heavy current policy scenario, the cost of electricity by 2050 sits at about 41 euros per megawatt hour.
All right, 41 euros.
But under the 100% renewable best policy scenario, that cost plummets to just 13 to 17 euros per megawatt hour.
Wait, really?
Yeah. Total annual system costs by 2050 are significantly lower in the green scenario, landing between 44 and 56 billion euros.
A drop from 41 to the low teens is a staggering efficiency gain. What is the actual mechanism driving that cost collapse in the models?
It hinges entirely on the shifting dynamics between CapEx and OpEx. Capital expenditures versus operational expenditures.
Right.
A renewable energy grid is incredibly CapEx heavy. You need massive upfront capital to manufacture and install the solar photovoltaics, the wind turbines, and all the battery storage systems required to balance the intermittency of the grid.
Because the sun isn't always shining and the wind isn't always blowing.
Exactly. But once that infrastructure is online, the marginal cost of the fuel, which is just the equatorial sun and the wind, is literally zero.
So the OPEX just drops through the floor,
Exactly.
whereas the fossil fuel model is a perpetual drain on operational expenditures.
It's precisely the opposite dynamic. The current policy scenario forces these emerging economies to remain permanently tethered to volatile global commodity markets,
Right. They are perpetually paying to import, refine, and burn coal, oil, and gas.
which means they're essentially importing inflation and supply chain vulnerability year after year.
That makes total sense.
By completely phasing out fossil fuels in the best policy scenario, they entirely avoid those compounding, continuous operational costs.
Even when the researchers factor in the expensive battery storage needed to balance a 100% renewable grid.
Even then, yeah, the sheer collapse of operational expenditures makes the green system vastly cheaper over the long run.
Okay, that structural advantage makes perfect sense for the power sector. You build the solar farm, the sun provides free fuel, and your long-term balance sheet improves.
Exactly.
But here is the massive hurdle the study has to clear. How do you actually apply that to heavy industry?
Oh, right.
Because solar power is intermittent. You can run a laptop or a residential grid on solar and batteries, sure, but you cannot run a 247 steel mill, a cement kiln, or a massive cross-ocean cargo ship on localized battery arrays. Batteries are just too heavy, and their energy density is too low for heavy-duty industrial applications.
You've hit on the critical bottleneck in global decarbonization. And to solve it, the study heavily models a technological framework known as Power to X.
The X being the chemical carrier you use to store and transport the renewable energy, right?
Correct. The power side of the equation is dominated by solar PV. The equatorial advantage of Kenya, Uganda, and Tanzania is so profound that in these models, solar provides up to 94% of all electricity generation by 2050.
94%, that is wild.
And the spatial footprint is remarkably efficient too. It requires less than 1% of the total land area across the KG region.
Wow, less than 1%.
Yeah. But as you pointed out, you cannot directly electrify a cargo ship. So you use that immense surplus of cheap renewable electricity to manufacture synthetic fuels and chemicals.
What we refer to as e-fuels and e-chemicals.
Exactly.
Here's where it gets really interesting, because we need to look at the actual mechanics of Power to X rather than just treating it like some high-tech black box.
Yeah, let's break it down.
We're basically talking about modern-day alchemy here, using that cheap solar electricity to power industrial-scale electrolysis, right? You run an electrical current through water to split the molecules and isolate green hydrogen.
That's step one, yes.
But hydrogen alone isn't the final product for most of these industries.
No, hydrogen is the vital precursor. It's the foundation of the entire Power to X ecosystem. But hydrogen presents a severe logistical nightmare.
Because it's so volatile.
Yeah, it is a tiny, highly volatile molecule. To store it or transport it across an ocean, you either have to compress it under immense pressure or cryogenically freeze it to near absolute zero.
Which I imagine is not cheap.
Not at all. Both processes require massive amounts of energy and highly specialized, expensive infrastructure.
So it's just not practical for global export from an emerging economy.
Right. So the study proposes taking that green hydrogen and chemically binding it with carbon to create a much more stable molecule.
And where are they getting the carbon?
Well, the solution modeled in the study relies heavily on direct air capture technology. You build massive facilities that literally scrub ambient CO2 directly out of the atmosphere.
That's incredible.
Then you take that captured carbon and combine it with your green hydrogen in a catalytic reactor.
Yeah.
And the output of that synthesis is e-methanol.
So e-methanol essentially acts as a liquid battery.
In a way, yes.
You are taking transient sunshine, using it to split water, grabbing carbon from the air, and magically creating a liquid fuel that you can pour into a cargo ship or pump through existing pipelines.
It perfectly bridges the gap between renewable electricity and heavy industry. E-methanol is a liquid at ambient temperature. It utilizes the existing global infrastructure for chemical transport.
You don't need to reinvent the wheel for shipping it.
Exactly. It can be burned directly in modified marine engines, and it serves as a foundational feedstock for plastics and heavy chemical manufacturing.
It's so versatile.
It really is. In fact, the study projects that e-methanol will eventually supply between 36% and 50% of the entire e-fuel and e-chemical demand across these three countries by 2050.
If the KUT region can master that synthesis, they aren't just decarbonizing their own local economies. They are transforming into a massive e-methanol factory for the rest of the world.
And the strategic implications there are just massive. This Power-to-X capability turns a geographic reality, being positioned on the equator with high solar irradiation into an unbeatable industrial advantage.
Because their primary input, the solar electricity, is so incredibly cheap.
Exactly. Their output costs for e-methanol will undercut almost anyone else on the planet. The modeling suggests Uganda will be producing electricity at just 11 euros per megawatt hour.
11 euros.
Yeah. Tanzania at 14, Kenya at 21. The global north simply cannot match those input costs.
Which brings us to the friction of capital, the trillion-dollar question, really.
Ah, yes. The money.
Yeah. Because the roadmap is brilliant,
Yes.
right? The chemistry is sound, and the long-term economics are undeniably superior. But building gigawatts of solar farms, industrial electrolyzers, and direct air capture facilities requires a staggering amount of upfront investment.
That's a huge hurdle.
The study estimates cumulative capital investments of between 646 and 732 billion euros by 2050 to build this fully renewable power-to-X system.
Yeah, that's a lot of zeros.
And these are developing economies facing brutally high risk premiums and borrowing costs on international debt markets. So where does nearly 750 billion euros come from to actually build this?
What's fascinating here is how the study frames this. The upfront capital requirement is undeniably the primary friction point. A nation cannot leverage itself into this level of infrastructure using standard sovereign debt without sparking a financial crisis.
Right, they'd go bankrupt before they poured the first foundation.
Exactly. So the study explicitly acknowledges that this transition necessitates innovative global financing mechanisms, specifically leaning on what we call blended finance.
Blended finance being the use of public or philanthropic capital to absorb the initial risk, making the project safe enough for private institutional investors to jump in.
That's exactly it. You have to de-risk the initial infrastructure build. This involves concessional capital from international development banks, green bonds, and deep international partnerships.
But the study frames this not as international aid, right, but as a mandatory strategic investment for the global north.
Absolutely. Because if East Africa defaults to the current policy scenario and scales up its fossil fuel usage to support 300 million people, the global carbon budget is completely blown.
The math just doesn't work for climate targets.
No. The global north needs East Africa to execute this leapfrog just to have a mathematical chance of hitting the targets of the Paris Agreement.
It is a shared global imperative, and the local macroeconomic payoff modeled in the study is enormous.
It's huge. Injecting this capital into a localized renewable infrastructure doesn't just build solar farms, it creates a profound economic multiplier effect.
Tell me about the GDP impact, because those numbers stuck out to me.
Yeah, the transition is projected to generate an additional 501 to 541 billion euros in cumulative GDP for the region by 2050.
That is life-changing money for the region.
It really is. It sparks domestic job creation, localizes supply chains, and crucially, it establishes an export market that will be desperately needed by Europe and Asia as they scramble for green marine fuels and chemical feedstocks.
So you spend the capital to build the infrastructure, you eliminate your reliance on imported fossil fuels, you boost your domestic GDP, and you end up exporting the green chemicals the rest of the world needs to survive.
It's a win-win-win scenario.
The thesis of this research is incredibly compelling. What we've explored today is really a rigorous mathematical proof that the future of industrialization does not have to be a repeat of the smog-filled 20th century.
Definitely not.
By harnessing insanely cheap solar power and pairing it with the chemical synthesis of power-to-X technology, East Africa can build a 100% renewable system that is economically and structurally superior to the fossil fuel alternative.
They really have a unique window in history right now to build the energy system of the future from scratch, completely unburdened by the legacy infrastructure that is currently slowing down the transition in the global north.
To you listening to this, thank you for joining us on this exploration of where the global energy supply chain is truly heading. We've been dissecting the insights from energy and economic leapfrogging, strategic pathways for sustainable energy industry transitions in East Africa's emerging economies.
It forces you to completely reevaluate the conventional wisdom of global development.
It really does.
And, it fundamentally shifts the paradigm. I want to leave you with one final thought to mull over, extending beyond the immediate techno-economic data in this paper.
Okay, let's hear.
If East Africa successfully executes this leapfrog, if they navigate the financing hurdles and utilize their equatorial advantage to become the world's absolute cheapest producer of essential e-fuels and green chemicals, how will this shift the global geopolitical map?
Oh, wow. The downstream effects of that would be massive.
Right. Because heavy industry is fiercely protective of its margins, and it always chases the absolute cheapest energy.
Always.
So if e-methanol and green hydrogen become the foundational elements of 21st century manufacturing, will we start to see the energy-intensive industries of Europe and North America physically dismantling their operations and relocating to the equator just to access this cheap, limitless green energy?
That is a staggering thought.
Are we standing on the verge of the global economic center of gravity, completely flipping from the global north to the global south?
So the next time someone asks you to imagine the future of global industry, and you reflexively picture a gray smokestack in Europe, well, you might want to start picturing an endless array of solar panels and catalytic reactors under the East African sun instead.